My name is Alyssa Whitcraft. I am a professor at the University of Maryland, but I'm also the Deputy Director and Program Manager of NASA Harvest, which is NASA's Food Security and Agriculture program. So, agriculture is the hallmark of human society. It's what has allowed us to develop all the other wonderful things that we have. It keeps every one of us alive, whether or not we are aware of our connection to the land that's being utilized to produce the food that we consume. Um, Unfortunately, every year since 2015, we've had increasing numbers of people who are food insecure, meaning that they don't have sufficient access to the food that they need that's of good quality nutrition, that's consistent throughout the year. NASA Harvest has three objectives, really, which is to increase our understanding of and also strengthen these things inherently, being agricultural productivity, agricultural sustainability, and in general, our land stewardship around agricultural land.
I am going to focus my talk today on the use of satellite data. After all, NASA Harvest is NASA's Food Security and Agriculture program, and we're all about utilizing Earth data collected in space for down to earth information on agriculture. So, satellite data, in case you're not aware, some characteristics are that it is synoptic, it's objective, it's timely, and it's repeatable. And these are things that all make it super valuable considering that agriculture covers about 40% of the land surface and changes meaningfully within days to weeks. That means it's really difficult to collect on the ground data, and it can provide a really important accompaniment to those field data that we can collect. I want to first emphasize up front we can't make satellite data useful without the ground data, but it still has a lot of value to add.
So, NASA began its investment in agricultural monitoring utilizing satellites basically from the very first satellites that were flown to observe Earth. So in 1972, they launched what became later known as Landsat 1, kind of colloquially, but its real name was ERTS 1 or Earth Resource Technology Satellite 1. And this was in 1972 that it was launched, close to 50 years ago now. And basically, some of the earliest experiments for the use of that data were actually partnerships with USDA and other federal agencies, and they were really geared toward understanding what was going on with agriculture in the world. If I can take a step back, I'll say what precipitated that event and that the need for that information critically was an event called the Great Grain Robbery. What happened was there was a grain shortage in one of the main bread baskets in the world, which is Russia, or at the time the USSR. And if I'm recalling the story correctly, they purchased a bunch of grain from the US. The seasons are kind of off, right? And so they purchased the grain from the U.S. And then when the U.S. went to go buy Russian grain, there wasn't any, and so we purchased back our own grain that we had grown in the United States for something like 10 times the price. And so there was a recognition that that couldn't have happened, that wouldn't have happened had we had knowledge about what was actually going on in the major agricultural areas of the world with respect to production. And so it becomes really critical to have the information that can be utilized to prevent speculation in the market and drive large fluctuations in the prices of crops. And satellite data are really useful for that. It wasn't until the sort of early 2000s that there started to be a shift toward recognizing that we're collecting this satellite data and sticking it in archives. And by not making it free and publicly available, we were really limiting its utility and its function. And so, with the vision of many people that kind of came to a head under the leadership of Barbara Ryan at USGS, they decided, you know what, let's make the Landsat archive freely and openly available for all of these different applications. And actually, that kind of precipitated some of the development of things in private sector like Google Earth and Google Maps that we utilize so heavily today. So fast forward, NASA's been investing in agriculture in terms of its satellite monitoring activities for about 40 years, come around 2011, 2012. And yet there wasn't a program to tie all of these activities together. It was a series of research projects and a series of research activities, but nothing kind of pulling the whole piece together to, which is often necessary to have vision in the future to push things really forward technologically. And so the folks within NASA's Applied Science Division, Lawrence Friedel and Brad Dorn, had a lot of vision here and said, we really need a program to push this forward.
We aim to improve agricultural land use, sustainability, and productivity by advancing our products and the underlying methods to produce the products, which again, these are public good, right? Because we are a NASA program, in 5 core areas: crop mapping, crop statistics, crop yield, crop condition, and cropping practices. So that's everything from where the agriculture is, how that's changing through time, what's going on with agriculture in the current season, what's going to be going on in future seasons, how are people utilizing their land, how has that changed over time. Those are all the kind of questions that we're looking for sort of physical evidence of with our satellite instruments and trying to understand large patterns, meaning, and develop actionable information. And we do this all over the world, from subfield to global scale. So highly, highly integrative and highly multi-scalar work with a lot of potential impact areas.
Agriculture is inherently sort of a private enterprise, and it's really critical to be able to partner with the private sector in order to kind of drive technology and agriculture forward. And that's not something that historically has been really easy for large federal agencies in the US.
Those goals that I laid out in that kind of trapezoidal diagram, we reach those through strong partnerships with folks from around the world working on a really large set of topics. I don't have time to talk about all of them today. So instead, I'm going to focus on what we're doing in our domestic agriculture work, and particularly what we do in sustainable and regenerative agriculture. This busy slide shows you at a glance what we are doing in the US. And there are kind of 6 areas where we focus, not geographical areas, but sort of thematic or impact areas. We work to support USDA, and that's not just in their domestic work, actually. We work with, Foreign Agriculture Service or Office of the Chief Economist, looking at what's happening worldwide, because we truly are a part of a global food and global climate system. So even what's happening in the US is highly relevant internationally, and what's happening internationally is highly relevant in the US. We also work a lot on private sector innovation. We have a lot of public-private partnerships and aim to sort of improve their ability to manage the land or the relationships they have with landowners in ways that are sustainable and resilient to extreme weather events and forward-looking into future years. And so a quick pause to say there's, not a real universally accepted definition of what it is for something to be considered regenerative. But the working definition that we have is a collection of locally appropriate cropland and rangeland practices, management practices that aim to stop and reverse soil erosion, enhance ecosystem services and watershed health, reduce the need for chemical and biological inputs, and contribute to increased farm resilience, productivity, and continuity into the future.
So there are many practices that farmers can take to more sustainably manage their crops. These include reduced tillage or no tillage. One of the techniques that farmers can utilize is cover cropping, which is applied either throughout the entire year permanently to kind of support general soil health, or applied during the winter to prevent the runoff of nitrogen and other fertilizers and things that have been applied to the crops.
And so I've listed just a handful of practices here. There's so much more than this. But what's really critical is we lack the methods to both detect the practices at scale and model their outcomes quantitatively at scale, not to mention the baselines. And so in this vein, because we know that we need better information at every level of the agricultural value chain, from inputs through consumers, we need this information to kind of empower the transition of farming at large scales to regeneration, healing the soil, healing the land community, which I attribute to Abe Collins, that phrase, and reaching net negative emissions. So this information really needs to be evidence-based, robust, synoptic, objective, timely, repeatable, those key characteristics of satellite data that I outlined at the beginning. And that's why we've sort of launched this Sustainable and Regenerative Agriculture Initiative, which is a public good, nonprofit, multi-stakeholder, pre-competitive forum that's really aims to make regenerative agriculture an implementable reality. And so it's pulling together common yardsticks, really driven by public interest, transparent science. And that's kind of what it's all about.
We do have to feed potentially 10 billion people by 2050. And we have to figure out a way to do it without endangering our native ecosystems, our natural ecosystems, and all of the different life that depends upon the land that we all share. And so, one of the things that remote sensing and satellite data can be really useful for is showing what works and showing what doesn't work in farms. If somebody adopts a new practice, does it have the desired outcome? So, if somebody wants to adopt no till, does it actually improve their soil health? Does it reduce the runoff of fertilizer? Making the value proposition to farmers as to why taking on new techniques that may be more complicated or require different machinery or inputs than they already have, they need evidence that it's not going to impact their yields negatively. They need evidence that it's going to have the outcomes in increasing soil health or at least reducing soil degradation. They need evidence that they're going to be able to manage their lands in a way that's going to be kind of coherent with the way that they've always wanted to manage the lands. And so, a really neat thing that remote sensing can do, because we have such a very deep time record, and it's also very synoptic, meaning that we can get large areas of coverage, is we can look at the impact of these practices over time. We can look for, first of all, the evidence of these practices occurring, and then look at, say, changes in yield that are experienced over time. If somebody institutes a reduced or no tillage system, can they rely on a decline in yields, an increase in yields? Will their yields stay about the same? And what about in terms of other metrics of soil health? Some of those things we can measure with remote sensing. A lot of them we utilize models in tandem with the remote sensing information to get to the bottom of that question. But essentially, we need to utilize all the data that we have in our hands to really build a strong evidence base that farmers would utilize to help make decisions about how they want to manage their land, and what are the pros and cons for their individual ecosystem.
So I'll give you a couple of examples of things we have going on. This is an example of one of the SARA projects. Jill Dines at Stanford looked at tillage intensity over 2005 to 2016, and then yields over the same croplands from 1999 to 2018, and basically found that no-till provided yield benefits, especially in areas with particularly dry summers, and those yield benefits were most commonly witnessed after about 11 years. And so that's an important consideration as well. You can't expect the yield benefits to come in straight away. This is another project we have with CropX, a private company. They have in situ soil moisture monitors. They're trying to figure out where in the field do we place them and how do we develop continuous maps of soil moisture across entire fields. Soil moisture is a critical input for farmer decisions about irrigation, for the applications of different crop protections, and for the prediction of crop yield. But it's not available at suitable spatial and temporal scales from satellite data. By fusing ground data and satellite remote sensing data, though, you're able to create higher resolution, hopefully more accurate and more granular looks at this that are highly valuable for farmer decision making. And then this is a brand new project that we have getting going in France. It's an evaluation of countrywide field scale nitrogen consumption. And it's really looking at satellite data over a number of fields in France to assess both where there's suboptimal fertilization and over fertilization, and looking at what the environmental and economic costs are, not just the physical, but also getting to the human dimension of the over fertilization in these regions.
This information can actually feed into a learning system that the farmers can rely on to help them understand, okay, if I take this decision at this point in the season, what are the expected outcomes? What can I look forward to? And that's something that remote sensing can really be useful in elucidating. we do have a genuine opportunity to both mitigate the changes that happen and improve our agricultural system's resilience to them. A lot of different pieces need to move. I mean, agriculture is fundamentally a human natural system, and it's a lot of private landowners need to be making a lot of decisions that are in their benefit, but also with the benefit of society in mind.
So I'll close by saying we're in a new era for remote sensing, for climate smart agriculture, for data integration and computation, for scaling and generalizing results, and for cross sectoral collaboration. And with that, I'll conclude. Thank you.